Hello students, Professor Nugent here. Let's talk about weak instruments and how the partial R squared can help us test the goodness of an instrument. Let's say that we have a first stage equation where y2 equals pi naught plus pi 1 times z1 plus pi 2 times z2 plus pi 3 times z3 plus u2. And the zi for I equals 1, 2, 3, these are our excluded instruments. Now we can test how good those instruments are using partial R squared. What is partial R squared? Let's define partial R squared for excluded instrument J as equal to R squared U for unrestricted minus R squared J for restricted all over 1 minus R squared R. Whoops. And that should be an R. So again, R squared U. This isn't the unrestricted R squared from the first stage, and the R squared R is the restricted R squared from the first stage, where the restriction is given by the null hypothesis that Zj is equal to 0 for j equals 1, 2, and 3. This null hypothesis would be tested for each instrument individually. So we're using this partial R squared as there is concern for the amount of marginal variation in y2 that is explained by these excluded instruments z1, 2, and 3. As long as we have some other explanatory variables in our structural equation, other than the instruments, we can use this partial R squared to quantify this marginal variation in y2 explained by the excluded instruments. This amounts to estimating an unrestricted OLS regression on the first stage and the restricted OLS regression on the very first stage with the coefficient on the excluded instrument set to 0. And then we obtain this partial R squared statistic. The range of partial R squared is from 0 to 1. So partial R squared will be greater than 0 but less than 1, where 0 implies too weak and 1 implies too strong, respectively. Let's look at an example of 3 instruments. And the partial R squared that we may have estimated for them. Z1, Z2, and Z3. These are our instruments, and then we have the partial R squared. Suppose that the partial R squared for Z1 is 0.001, the partial R squared for Z2 is 0.5, and the partial R squared for Z3 is 0.999. The first instrument, Z1, explains very little of the residual variation in the endogenous explanatory variable once the variation in the other exogenous variables are partialed out. As such, Z1 would likely cause the first stage to suffer from a weak instrument problem. The third instrument, Z3, explains nearly all of the residual variation and would not likely suffer from a weak instrument problem, but raises concerns of exogeneity. If Y2 is correlated with the error term in the structural equation, which is the assumption of endogeneity, then Z3 almost surely is endogenous as well, assuming the other exogenous variables are really exogenous. So this case of Z3 could be considered a strong instrument problem. The second instrument, Z2, explains some, but not all, of the residual variation in Y2. Z2 would seem to be the best candidate, then not to suffer from neither a weak nor a strong instrument problem. So we can determine which instruments to include using this analysis. It is obvious that we should include Z2. We can consider including Z1, particularly if it is not strongly correlated with Z2. We should still report the first stage F statistic in partial R squared. With F included, with Z2 included, the model will be over-identified, and we could also do an over-identification test. Because the partial R squared is so high for Z3, it is hard to believe the exogeneity assumption holds for this instrument and so should not be included. One final word: the worse the instruments, the more we need to worry about making things worse doing instrumental variables. That's it for partial R squared. Stay tuned to the next video. We will discuss finite sample bias.